is just give a quick overview of some of the terminology and concepts we're using with these LID calculations, and then go into how we size probably the most popular single LID, which would be the rain garden / bioretention / bioinfiltration. There's a bunch of names for the same thing. It's just because the concepts have come from a lot of different directions, and so and it's not because if we make it sound more complicated, we can charge more. Very little of the renaming has come into that. So when we're dealing with our sizing for these systems, there's a number of critical elements that we're looking at as far as the design for these. The drainage area, we've already worked on some of these. It's the drainage area. I'll put the common abbreviation, DA. We got that down pat, or we're getting there, right? We understand what that is. All right, we're going to have our design storm. That's going to be our 1 inch or our 1.7 inches. Our, what depends on our locality. This is just sort of some of the mathematical pieces that we're going to need to know for sizing pretty much any LID. We're going to need to know what what is commonly called in the regulations the treatment volume. And in Virginia, at least, that's big T, little v. The treatment volume is what you've already been calculating off. That is the runoff volume. That's what we calculated for the church project. So different name, same thing. And that can be most commonly in cubic feet, although sometimes for doing rainwater harvesting, something kind of tank-based, we might calculate that in gallons. Same thing, different units. Okay, so we've already got all of this down pat. Right, so we can figure out how much water is going to the thing. So how do we size the thing, the BMP? Well, I'm going to go into this specifically per the BMP, but there's some general features that we're usually looking at. And I drew our, don't want to get too far away from the film crew here. I drew our section. Drew our typical section earlier when I was talking about under drains. But we've basically gone out, we've dug a hole in the ground. We're going to have a BMP located here. So maybe we're going to have permeable pavement, which we'll talk about this afternoon, which would, kind of the surface of it might be up here. It might be a rain garden where the surface of it, we have a ponding depth, and I'll talk about a rain garden in a second. But we will have some volume, or we'll size this to handle our treatment volume. So whatever volume we decide we want to manage, say the 1 inch storm going to this BMP, we will size it so it can hold that entire treatment volume, if at all possible. Okay? There might be a case, again, a lot of the Rainscapes designs, the residential level, are designed to manage less than this. And a lot of those are sort of, as I mentioned in the slides I talk about, there's mandatory regulatory projects, and there's projects of opportunity. A lot of those are projects of opportunity. So they say, we've got a grant, we can pay you to this much for a rain garden on your site, and you just manage what you can. But in our case, we're actually going to try, what we're going through is designing to the treatment volume. Okay? So what we need to know for each one of these features is what is the treatment volume for a rain garden, a permeable pavement, or a cistern going to be. A cistern, really, I can tell you now, you're going to need a tank that's pretty much equal to your treatment volume, right? So that one's easy. The only thing there is sometimes, usually we'll assume that the tank isn't completely empty when it starts to fill up. So we might make an assumption that we'll assume the tank is half full when it starts raining, and we want enough volume to hold that. That's just an assumption we can make. But so with a tank, real simple, because it's completely hollow inside, right? But our other features are going to have multiple layers in them. You can call it the drainage layer. You can call it gravel. Drainage. If you want to charge more for it, you can call it aggregate. Okay, so a lot of names is we're talking about basically, as I mentioned earlier, open graded stone. So number 57 is a Department of Transportation standard that we pretty conveniently use. We'll use different grades from different times, but in general, we want a stone that's open graded. Water will flow through it easily. Then above that, if it's bioretention, we're going to have this stuff. So some kind of bioretention mix, rain garden mix, again, a lot of different names. But this is, if you remember the first day when we did our little soils lab, and I took a whole bunch of sand and I kind of took a handful of compost and chunked it in the sand and mixed it up and said, this is my homemade bioretention mix. That's what you're looking at. This is going to be essentially a well-drained soil that's fairly high in organics. And we'll, as we get into the rain garden, we'll talk more about the specifics of that, and there's a lot of specifications. But you've got, in a rain garden, you've got some form of mix here. And then, again, this is typically for rain gardens. You've got this layer up here. It's your ponding. Layer, right? It's been raining. Your rain garden is designed to hold, say, 6 to 12 inches are typical ponding depths. So it's designed such that when it gets more than 6 inches, it goes out in overflow. So basically, when it stops raining, you're only going to see 6 inches in there. That's your ponding level. So when water flows into this, figuring out how much volume we can have is going to depend really. Gravel takes up space, right? All that bioretention mix takes up space in this hole. It's not just the water, you don't just size a hole based on how much water you need, because you've got to figure in your amounts that you have of these various mixes. And so to do that, there are commonly accepted void ratios. You can tell the engineer's got a hold of that one. And so that's just a measurement of how much open volume you are typically going to get when you've got an installed feature there, and then you're going to fill it up with water. So with gravel, it's pretty easy to picture, but if you kind of blow it up in your mind, instead of thinking about little bitty gravel, if you think about like riprap, the stuff you see along the sides of the highway where you got the big pipes dumping to it, if you picture like a big clear box that's full of those stones, you can see where the air spaces were. You can see if you filled that up with water, you'd be able to see the water in and around the rocks, right? Same thing happens at essentially the same proportions, no matter what your stone size is, as long as it's an open graded stone size. And the number that we use for drainage layer aggregate is a void ratio . I don't know, actually let me put it over here. Can you see it if it's over here? Gravel is 40%. The void ratio. So that means if you had a 1 cubic foot box, clear acrylic box, you filled it up with number 57 stone, shaky, shaky, shake it, level it off, it's completely filled with number 57 stone, and it's 1 cubic foot of stone. If you fill that up with water, all the way up to the tippy top, then to drain the water out, you would get 40% of a cubic foot of water coming out of that. Okay? So that's how much water fits in and amongst the voids here. So that's what that void ratio, you basically have gravel, it's 60% of that space is gravel, 40%, which is the only part we care about, is actually water. So when we say this is a void ratio for a gravel bed, that's the space in and around those rocks where the water can be stored. Does that concept make pretty much sense? Okay.
Yeah, and how much gravel did you say it was?
Gravel itself. 40%. It's going to be 60%. The rest of it's gravel. It's all gravel and water, right? There's no air bubbles in there.
So it doesn't need to be a certain amount, as long as we get the 40%.
Well, that's what you always get. So when we're dealing with gravel in any of these BMPs, we're going to have 40% of that volume where the gravel is going to be our storage volume.
So for 1 cubic foot of space, like filled gravel, really only 60% of it is gravel.
Right.
40% of it is coarse.
Right.
Oh, I'm sorry.
That's just like a multiplier.
So for 1 cubic foot of space, you have a 1 cubic foot container, you fill it with this particular kind of gravel, really only 0.6 cubic feet is gravel, 0.4 cubic feet is pore space that can be filled.
Yep. And it doesn't matter, I've had the question come up of, because we use different sizes of gravel, there's a number of different stones, and I talk about it in the lecture. The ratio is constant, whether it's what we call a number 7 stone, which would be small, number 8's like aquarium gravel, little bitty, number 2 stones are the good ones. If you want to chunk a rock through a window, that's like railroad ballast size, number 57 somewhere inside. They all have the same ratio. I assume some graduate student at some Polytechnic University has proven this, and there's probably variations, slight variations, but for the purposes of this class, it has been carved into a tablet near a burning bush that the void ratio for gravel areas is 40%. In the regulations, they do not differentiate, so I'm assuming it's pretty darn close no matter what kind of stone you use. Okay? But yeah, but when you think about little bitty stones, you have thousands or millions of little bitty voids, and it's not that hard to prove because you know how much gravel weighs for solid gravel. So you can fill a container with it, weigh it, and say, oh, if it was a rock of this material, if it was solid limestone, 1 cubic foot rock, it would weigh this much. It doesn't, it weighs less. The difference is the void ratio. So it's pretty easy to measure, so I'm assuming it must be pretty darn close. I'm taking it on faith.
So it has more to do with the shape.
The shape and the gradation of the stone. So that's why it has to be that open graded stone that I talked about. So number 57, number 7s, number 2s, there's a lot of different ones out there. Number 57s and number 7s are the 2 that I'll be talking about in this course. Okay? So that's our aggregate void ratio. So next we have our biomix. I'll put it in blue because it's bio. All right? So anyone want to guess? You've got that sand with the compost. What kind of void ratio that might have? How much water is going to be fitting in? Or it's not too far from it. It's actually a little bit more than that. So 0.25 is the void ratio for the biomix. So it doesn't seem like it. It's kind of counterintuitive. It seems like, well, there's hardly any room for water, but 25% of the volume that you've got for your rain garden mix, if you're using a BMP with rain garden mix, is going to be available for storing water.
And is that because it's absorbing, and so you're actually cutting the pore space like inside the compost?
It's a combination of, some of it is kind of spongy material like compost, which is like a sponge. Water actually soaks up into it, and then some of it is on the I won't say microscopic level, but on the teeny tiny level. If you look at that sand that it's made of, they specify a sand that where you don't have clay, you don't have these really tiny particles. So if you were to put it under a magnifying glass or a weak microscope, you'd actually see it's very much like the gravel. It's got a lot of angular stones that have gaps between them. on the eensy-weensy level, I think is the technical term. So we've got a 25% void ratio for our bioretention mix. And then last, the easiest one, our ponding. Correct. That seems obvious, but it's not to everybody. So that's basically an empty container of water can hold the entire volume worth of water. Okay? So these ratios are used not just in this class, but I think Maryland, DC, everywhere, and Virginia all use these same numbers. So I haven't yet to run into a reference that varied from these. So these are about as constant as we get in this business. Yeah.
What about
Plants do not, we don't figure into plants. So if we're doing bioretention and we're planting trees and grasses and all that, we ignore them. So we also ignore the space they take up in the rain garden. So we design the volume of the rain garden, which is what I'm going to step into next, without figuring the plants in them, which from a realistic standpoint may or may not be correct. I mean, more plants is going to take up more space, so there's less space in there for water, but more plants are going to have more uptake. So it's pretty much of a wash. But for actual design, and for the purposes of this class, plants don't exist until after we've done our calculations. So we calculate a big naked rain garden as far as volume and sizing, and then we put our plants in. So this is a pretty simple, straightforward concept, but it's also one of those critical concepts that if you don't get it, now's the time to say something. We can make sure we address that, because this is the basis for sizing all of these features. Okay?
If anybody doesn't understand what Chris is talking about, please raise your hand now.
I just want, you sometimes say, when you say a 1-inch storm, is that the same as saying a one? Because I read a lot of regulations that don't say inches, it says
Years.
But you keep saying a 1-inch
A
storm.
1-inch storm is Virginia standard.
Okay.
The actual 1-year storm, if you remember last class, I think we went on to that site from NOAA. That 1-year storm is going to vary throughout wherever. It's going to be specific to your research. So you're going to have a different 1-year storm than Jeannie would have where she lives. So that's going to vary. But in Virginia, statistically speaking, they decided the 1-inch storm, it was a combination of, we need something that's actually buildable and affordable so the developers their heads don't explode and they don't, have all our regulations, basically kill the regulations before they get approved, because there's always that compromise. And statistically, the 1-inch storm in Virginia is 90%. Now this is statewide. 90% of all our storms in Virginia are 1 inch or less. That is less than the 1-year storm. It might be probably if we looked back at that NOAA thing with all that data, it might be the 6-month storm or the 3-month storm or something like that. So, but you can design these to any storm. So this is just one of your variables. So you can design the same features using the same methods, and all that changes is that variable that you use to calculate your treatment volume.
So, I guess I'm asking because my city says I have to do a 10-year storm design. So how do I have to go look up and see I got to look up a table for the 10-year?
You can look on that.
Right.
You can look on that NOAA site, but I'd go back and check that, because pretty much every LID feature I've seen or best management practices, same. Again, we got to use different names for the same thing. But the 10-year storm typically is designed or is required to make sure that much flow can go through your BMP, but that is not your treatment volume. I've never seen anywhere that's treating the 10-year storm. So there's two different.
It's saying minimum design
But maybe
frequency.
it's saying that you have to design it so that the 10 years storm won't wash out.
Right. So if you design this, with overflow piping, like these ones I just did for these River Smart schools, DC is the only place, I think, in the entire planet that requires a 15-year storm. Lots of luck. All that data on the NOAA site, they don't even do a 15-year storm. So basically go to DC and say, what do you guys consider a 15-year storm? Here's the magic number, and you plug that number in. But that storm is really just, I have overflow structure, so the rain gardens fill up, let's just transition to rain gardens. I'll touch on that as I get into the rain garden design. Okay? But that is more of we'll design these features at two levels. The first level is to capture this treatment volume. And that is for our low-level, work-a-day, average, everyday storms, which is where the vast majority statistically of our pollutants are coming from throughout the year. Then we will design them to a larger storm just to make sure that when that 10-year storm hits your facility, that it doesn't wash all your plants into your neighbor's yard, or you've got, such a small pipe that it backs up and floods and goes somewhere unpredictable. So there's two different design features there. One is to basically protect the rain garden and the property around it from damage when you get that real gully washer. These best management practices do very little, although when you have thousands of them in an area, it all adds up. But on a given site, when you run the calculations, it always surprises me how little impact they actually have on like the 10-year storm. They reduce it down a little bit, but it's tiny because they're not designed to capture these huge volumes. They're designed to catch these smaller storms and treat those. So I'm going to move on to rain garden design. And in the lecture and in the, I'm going to write these void ratios back up before I start that. But in the lecture and in the BMP, bioretention is what Virginia calls it, clearinghouse guideline, that PDF that I loaded earlier. Like I said, tons of details, tons of factors. I'm just going to touch on some of those here. For our void ratios, gravel, 0.40, mix, 0.25, ponding is 1. Okay? So we're designing a typical rain garden. And here's our rain garden section. This is our, what we usually call out as undisturbed soil at the bottom of our hole here. So just one, I am going to touch on a couple of critical rain garden construction issues just because these are things that you can commonly see and can make or break the function of a rain garden. So when you're excavating out the rain garden here, this is where our infiltration is going to take place. We dig a hole. So right now we haven't put anything in there, right? We dug our big hole, but when you think about it, when it rains and this hole fills up with our water, this is where our infiltration is going to take place, right? So these, what we will call subsoils. So the stuff we pull out is soil. The stuff that's left, the dirt you see at the bottom of the hole, we call subsoil. That's where our infiltration takes place. So this interface right here, that surface of the dirt that you see when the guy or a gal on the big machine is done digging a hole, that is the surface that your rainwater is going to see. It's extremely, extremely important that that surface be dug in a manner that is conducive to infiltration. So I don't expect y'all to have any great construction knowledge. I'm sure some of you have a lot more than me and some of you have none. But in basic terms, on their digging machine, usually it's like a backhoe, a mini excavator, which I like driving those, those are fun. And then they've got the big excavator. But basically, you've got some kind of a bucket that's going to dig this thing out. For the bioretention basins, we're not talking about the ones you're digging by hand, typically. So if they have a smooth edge bucket, which is exactly what it sounds like, it's a scoop, and the edge of it's nice and smooth. It's like a knife's edge in the bucket. And they dig down with their big bucket, and they get that, and they drag it across, and they pull it up. What's that surface going to be like? Smooth. And actually, a sign of a great equipment operator is they can leave the bottom of a big excavation as smooth and flat as a pool table. It's beautiful. And it's horrible for BMP because if you have any clay in your soil, as you probably know, we talked about when we did the infiltration test, if you have any clay and you smear it, you've basically sealed this off. You may as well lay a piece of plastic in the bottom for all the infiltration you get. So you did a great design, you picked the right plants, you designed the right thing, you did your infiltration test, and because they didn't know what they're doing. The person running the excavator just screwed up your entire rain garden right there. And it may still work, but I like to give, it's sort of like raising children. You don't always know at the time what's right and what's wrong, what's going to make a difference. But I want to give my child here, my baby, every chance that I can to succeed. So I want to make sure that this surface is rough. So I will require them to have a bucket with teeth on it. They have some that they can actually just attach to their bucket, or they change the bucket. It's not a big deal for the contractor. But if that bucket's got teeth on it, then the surface it leaves is nice and rough. I want that surface ugly and rough. And I've come in and had contractors and said, that hole is absolutely beautiful. Now put a bucket with teeth on it and rough it up. And I mean, I've had operators I thought were going to cry. And, a big man with tattoos and, a funky, ZZ Top beard, seeing them near tears is a sad thing. But part of my job is to explain, this is how it works, And once you explain politely, this is what's got to happen there, and they understand. That kind of goes with that contractor training. Once they understand this is what has to happen, you need a rough surface. If water won't soak down through that surface, it's not going to work. They're like, oh, well, I can do that. So it's a matter of training. Yeah.
So I'm guessing the same goes with the side.
The sides don't really matter.
Okay.
Because if you remember with our correction thing that we did, our rain gardens tend to be really big. And there's the other side.
Even if it's like a dry swale.
Typically, we're not, if you've got a swale and you kind of dug it, normally when we dig it, I want as much bioretention mix as I can. I want as much volume as I can. So it's typically going to have straight sides. Actually, when we dig it, we kind of dig it like that, and then we'll put some, we'll ramp up the bioretention mix or put gravel or something there to give a smooth transition. But for all intents and purposes, all of our infiltration is really happening through the bottom, and we ignore the sides. In some cases, if we've got some kind of a construction over here or a building over here, I might actually take a piece of pond liner and intentionally run it down that side, maybe along the edge, to create an impermeable barrier so water can't get over here and screw up a structure. But that's kind of advanced rain garden stuff. But the sides are not that critical. The bottom is absolutely critical. Yeah. Yeah, if we're doing under drains, that's a different, but no matter where they're digging it, whether I'm going to have under drains or not, whether I've done my tests and my soils are crap or not, I'm still an optimist. I still want to, there's no reason not to leave that surface nice and rough. There's no advantage to having a straight bucket and a smooth surface on that. It doesn't do anything good for you. So I'll still want that surface rough. Sometimes you get a pleasant surprise, but we've had rain gardens, one that Lauren and I did last year, that the infiltration looked like it was little or nothing. We kind of designed it that way, but when we actually went out in the field and looked at it, it looks like it's actually draining down a lot better than we expected. But when they built it, we gave it every chance to infiltrate. So that subsoil, really, before we have any materials in the hole, that's our first critical material. All right, our next, we're going to have our aggregate. I was calling it gravel before. Let's stick with gravel. No need to get uppity. Okay, so we're going to have some depth for gravel. And I'm going to just up here put, we'll call that DG, the depth of gravel, because why not? Okay. Then we're going to have our bioretention mix, which of course has to be green on the whiteboard. And that'd be what there's nothing magic about these initials. I'm just putting them down here to have something to reference to. And then what's the last piece we're going to have on the very top? So ponding depth, right? So ponding DP. What the heck? If I called it something different, the lecture, go by the lecture. It's online, but the math all works out the exact same. Okay? So we've got 3 different depths for a rain garden. If you want, well, what sets the top of this? Water is always going to seek a level. We all know that intuitively, but we can get kind of screwed up on, well, where's the water going to be? And I've found myself at times trying to will water to be uphill. Water is always going to seek a level. So at some point down at this end, at that exact level, maybe we've got a big pipe that's open on the top, and that water flows into it and goes out. Or maybe we've got a berm and it runs over, but at some point you've got a controlling elevation, and that is exactly what's going to set this point. So when I want 6 inches of ponding depth, if I know, this surface is all flat, all these surfaces are dead flat across the entire site. Doesn't matter if the site is sloping, all these are still flat. You just may end up with a high side and a low side of where you have to dig it out. Water won't go uphill. I never, ever have anything where my subsoil has got any slope at all. Dead flat, dead flat, dead flat, all the way across. Now in reality, your rain garden mix is going to settle and stuff. You'll end up with a little lumpy stuff, but essentially it's all seed elevation. So I want to figure out how much volume I can get in this rain garden, right? For a given depth. Well, I know for my depth of gravel, and I know my void ratios for my gravel, my biomix, and my ponding, so not the river. And so the way I do it, everybody does it a little bit different. You can kind of size, you can assume some depths, and say, well, I'm going to start with, say, 12 inches of gravel. 18 inches of biomix is 18 to 24 inches is a pretty common minimum in most localities. Ponding depth, 6 inches, and I can say, okay, well, I'm gonna start with that, and then if I draw this thing on the sides and I can plug these numbers in and use the void ratios, and I can see if it's too big or too little. And if it's too big, I make it smaller. If it's too little, I make it bigger. And you go back and forth and back and forth. I'm lazy. I may have made that point. I don't want to go back and forth and back and forth. I want to do one calculation. So the way I do it, and this is just my method, you're free to do it whichever way you want, is I figure a unit rain garden area. So my unit area. All right, well, let's call it a unit volume. Sorry about that. I can use my eraser. All right. And I just find this a very useful tool. So here's the way a unit volume works. I think of 1 square foot of rain garden area, 3-dimensional. Okay. So forget my 3-dimensional. If I had a plexiglass column here, 1 foot, flat bottom, and then it had clear sides, right? So I can fill it up to whatever height I want with these different mixes. And I know my void ratios, so that is my unit volume. So I know 1 square foot of rain garden will hold a certain amount of water based on these. And then I can do one calculation. I say I need to know how much, I know I have to hold 1,000 cubic feet of water. What's my square foot of my rain garden? I do one calculation. So here's how that unit volume works. I'm going to take my depth of gravel times the void ratio. Let's see if I change. All right, void ratio of gravel, which is that's 0.4, right? That's going to give me the volume of gravel I've got, and this is it's in one. This is per cubic feet. So I've got, this is on a 1 square foot basis, so I have to multiply that times my depth. So this doesn't give me, this is on a 1 square foot footprint. I need to multiply that times my depth to get it 3 dimensions, to get cubic feet, right? So my depth here, I'm sorry, that's my depth. That's my void ratio. That's right. No, that's right. So I've already got that.
And
So
it's by the surface area that it's on.
it's for the surface area is 1 square foot. So again, picture this 1 foot square column.
Ice cube tray.
It's like a very tall one, maybe. Yes. And times my void ratio. This has to be in feet, because we want everything end up being in cubic feet, right? We're dealing with cubic feet. All right. So my void ratio that I've got in the gravel section plus, so that's how much water I'm going to hold in here. Plus the depth of my biomix times the void ratio of that. So B times B plus my ponding depth. Right, and the void ratio is 1. If it makes you feel better to write it in there so it doesn't feel sad, it's in there though. So we know these numbers here, 0.25 is our void ratio for our biomix. Okay? So here's how that works out. Let's just use the numbers I already wrote on here, and somebody with a calculator help me out. So we've got 12 inches of gravel, so we convert that to feet, right? So that's 1 foot. I can do the math for the first one by myself, okay? So that's going to be 1 times our void ratio, 0.4. All right? Does that make sense? All right, then our depth for our biomix in feet, 18 inches is 1.5 feet. 1.5 times our void ratio, 0.25, plus our ponding depth, again in feet, so that's 0.5, 6 inches. And my writing's getting worse and I get more off at an angle. Does that, everybody see where those numbers came from? Yes? No? Yes? Okay. All right.
Where's the 0.5?
That's my ponding depth. So this depth of ponding is 6 inches. Everything has to be in feet.
6 inches?
6 inches is 0.5 feet. So all these,
Oh,
these are all of these depths have to be in feet. Because everything we're calculating is cubic feet.
so you took each of those and divided by 12. Each of those
Right.
numbers and divided by
Yep.
12.
So 12 divided by 12 is 1. 18 divided by 12 is 1.5. 6 divided by 12 is 0.5. Okay? So what do we get for our unit volume for this particular design?
1.28.
1.28. And what would our units be for this, for those of you unit-minded? Cubic feet per square foot, right? So we can hold a little over 1.25 cubic feet of water for every square foot of rain garden. Okay?
Interpret that again, please.
So
1.28 cubic feet of water for every
Square
square
foot.
foot of.
of rain garden.
Of surface
Yeah,
area.
because we started this unit is for a 1 foot footprint, and it's how much as we use these different mixes. So that is our unit volume down there. I don't know if, can everybody see that or see where it came from?
This might be getting ahead of things, but so, imagine then you adjust based on the surface area you have available and how much water you want to absorb. But is there, you used a ratio sort of 1:3:2 for ponding, biomix, and gravel. Is there anything magical about that ratio?
No.
Because obviously you could adjust by
These are
saying
very
one-
these are very typical numbers, and that's actually something that the homework, and we'll work a little bit on class assignment. We're going to look at different ratios because you can use different ratios. These are pretty common, but don't feel like you have to be locked into those. So that's a nice thing. For these particular ratios, you're always going to have this unit volume. And that's actually written into some of the regulations. So I have like this magic little factor, and they say you take this. Really, that magic factor is just unit volume for sizing certain things. So let's say we have a rain garden volume that we need to treat. So we went through, actually from who's got their homework with them from this morning? Yeah. So what was our volume for downspouts 3 and 4 in cubic feet? Does anybody have that?
3 and 64.
All right, so 3 plus 64 plus 7, 157 cubic feet between the two of them. Does that sound right? We're going to find out how badly I sized that rain garden that's there, okay? All right, so we're 157 cubic feet. So that's for my 1-inch storm. We determined how much runoff we got to our area where we're putting our rain garden. Now we want to size and see for this specific design of aggregate biomix and ponding, how many square feet would that need to be? All right, so how are we going to do that calculation?
57 divided by 1.28.
So it's our treatment volume. Remember, that's what we talked about. This number is our treatment volume, right? So it's our treatment volume divided by our, what do we want to call this? Our unit volume. Will give you your rain garden starts with an R, rain garden area. And if you look at the units, that actually works out. So let's write that out. We've got our treatment volume for this is 157 cubic feet divided by 1.28 cubic feet per square feet. And what did that number turn out to be?
123.
123 square feet. And so this is on the bottom, but it's actually on the bottom of the calculation. So it ends up being so this I didn't measure that rain garden, and I actually don't remember. I think I had a lot more gravel than that under that rain garden. So if it's too small, yeah, I made up the difference in gravel. But that's how you would size a rain garden at the very, very basics.
Christine says you can get it.
Yeah, the one on the right is 140 square feet.
Bigger is always better. I think we still put in a lot more gravel and biomix because I remember those holes were like 5.5 feet deep. Because I wanted to have a lot of holding volume because I couldn't put an under drain there. There was nothing we could make through. We had a big, I think it was a pin oak. Are pin oaks things I'm allowed to cut through the roots of?
It was a tulip concrete.
Oh, was it a tulip? Oh, a tulip. That was on the no-no list. So I did not put in any under drains. And I knew, I had no overflow to pond this too.
Yeah, it was
We-
right next to the driveway.
Yeah, so it just ponded right back where it used to pond before we built it. So that sort of falls under, as far as liability, there was nothing I could do that would make the situation worse. I knew my soils would perk, and so we put those in. So everybody see where those numbers came from? Yes? No?
Where did you get 157?
That was, we looked back at the homework from last night and we added up downspouts 3 and 4. So that was my total volume going to this rain garden. Yeah, Dave.
I'm a little curious how we got our desired depths for the gravel biomes.
These are pretty typical numbers, but you can definitely use different numbers, and that's what we're going to do next. So
So is that
Relate to your soil.
the suggested ratio?
no, there's not a suggested ratio. Here's if you want to write something down as far as typical ranges. Typically, your rain gardens are going to be at least 6 inches. This is for larger rain gardens. 6 inches to 12 inches of ponding depth. The minimum biomix that I've seen in any regs, I think Virginia's micro bioretention in DC is 18 inches. So that's a difference. If you're doing a residential rain garden, you're not going to have 18 inches of design biomix in there typically. A lot of times they're digging out the soils they've got, amended a little bit, and have some ponding depth. So, but this is for the fully designed regulatory bioretention area.
And you said that was typically 18 inches
18 inches minimum.
minimum.
To 18 to 24. In Virginia, if you're going to what's called a level 2, where you get more treatment credit, 36 inches of bioretention mix. So you're talking about projects. Like I'm working on a project right now that I'm just starting on the design for it, my new shiny job. They haven't fired me yet. And we're probably going to be looking at like 5 or 6 tractor trailer, dump trailers of bioretention mix. And we're going to be talking about hundreds of cubic yards of mix.
Where is it?
It's in Louisa, of all places. So it's actually a very unenvironmental site. It's an industrial park, and they're flattening out a big pad and doing a lot of pavement, a lot of buildings, but we've got to manage the stormwater. And so we're using a series of rain gardens and level spreaders. So.
In the 18-inch minimum, you just account for the root requirements.
Right, you want to provide root requirements. You also want to deal with sort of what Alex had mentioned before. You want to have some buffer in there so as you got all these pollutants coming in, your soils aren't getting saturated, your plants, have something to eat and to drink. Because that gravel layer, that's dry, basically. So if you just have a thin little amount of bioretention mix on a big gravel layer, it's basically like it's hitting the air at that point. It's not getting, it's not getting what it's going to need for a plant thing.
So the gravel, how much would that typically go for?
Usually, I don't put in anything less than about 12 inches. So there might be specs, you might be able to get by with 6 inches or so on a small system. I usually put 12. But let's try a different mix.
I
All right,
want
we're
to
gonna-
ask one question too.
Uh-huh.
With climate change and the storms getting more intense, should we not be dining for more than a 1-inch design storm?
Again, you're talking about the amount of the big storms. I'm not sure if our annual rainfall, which is what these are designed to treat, is significantly changing. Now, the odds of your rain garden getting washed away might be going up, but that's sort of beyond my knowledge to manage. So at some point they may change that. But anyway, let's look at this real quick before we break for lunch. Lauren's over there with her timer. So let's try a different mix. Okay, let's remember we still have 157 cubic feet that we need to treat, so that hasn't changed. But this time we're going to have, let's go with 18 inches of gravel. Let's go 24 inches of biomix and 12 inches of ponding. So what's this? Just looking at these numbers, these are all, how do these compare to the ones we just had? All bigger. So what's going to happen to our footprint of our required rain garden? It's going to shrinky dink it, right? Does that make sense? So we can hold more water in our unit square footage, and so we're going to not need as much square footage. So let's see what those numbers are. Our gravel is going to be what? What's our depth of gravel in feet? All right. Times, what does that have to be times? 0.4 plus depth of mix in feet, 2 times what? Plus our ponding depth, which is 1, right? Everything's got to be in feet. Okay? So what's our unit volume? 2.1? That's cubic feet per square foot. Okay? Does everybody see where that number came from? So we increased our depths, and the gravel is going to make the biggest impact because it's got the biggest void ratio. Well, ponding's the biggest impact. Increasing your ponding depth is huge. Gravel's next biggest, fire retention is less. But we add them all up, 2.1 cubic feet per square foot. We've got 157 cubic feet to treat. I apologize for being in the middle of things, but divided by our 2.1, right? So how much square footage does this one require? 58. Different. So a much same amount of treatment volume. 75, up, 75. Still a big difference.
Oh, yeah, you're right, sorry.
One has an Android, one has an iPhone. Did you match? All right, 75 square footage. Still, we haven't quite dropped it in half, but it's a significant reduction. So you see how handy, even though DOEE, their brains explode when I've tried to show them calculations this way, and I just toe the line. I designed it this way, and I plug the numbers into their spreadsheets so they're happy. But you can see how handy this tool is. So say you could actually do this backwards if you wanted to, and you can say, I've got a 100 square foot area that I want a rain garden. I want to optimize it. And so rather than going back and forth, you could start with this number, and you already have your design number. I'll make that over here. So if you wanted to find out what your unit volume had to be, just rearranging that equation right here is going to be, our unit volume is going to equal to what? Who remembers 9th grade algebra? Nobody?
Volume divided by the area.
All right, very good. Treatment volume divided by the rain garden area. So if you knew I want a 100 square foot area and I know my treatment volume, you could come up with, well, what's my unit volume? And then you could play with these ratios, you know, plug them into a spreadsheet, however you wanted to calculate those, but you could actually, you know, optimize that, or at least check your numbers and make sure that they would meet that. Nothing wrong with going bigger. And in many cases, as you can see from the difference in the design storms, Maryland's going to have a design storm that, is it like 2 point, for Maryland?
2.6.
2.6, so that's over 2.5 times bigger than Virginia's design storm. We're not that far away, but it's a change in how the municipality wants to look at the sizing. So you can definitely make it bigger. I would not go below the 1 inch because you're getting to the point where if you're going to all this work of digging the hole and buying the biomix and building this thing, you want to have an impact. It is possible to drastically oversize these, and if you get too big, depending on your design, you can basically have plants that never, at the far end of a really large rain garden, that if it's way over designed, that may not get enough water, and that soil is really well drained, so you can actually run into some long-term maintenance issues if you get really carried away for sizing this. But you've got some latitude here. Okay? Any questions on that before you go and eat a delicious lunch? All right, great. So, did you have anything before we break for lunch?
No, let's take an hour for lunch, be back here at 1 o'clock.
If you have your homework that we went over earlier, if you want to give that to me now, then I can look over, check it off, and give it back to you by the end of the day. So